Hello, this is the interim presentation for Team 2. My name is Nick, and I will be accompanied by Zach, Khalif, Luke, and Aman.
Hi, I'm Khalif Adigay, and I'll be starting off our presentation with our product description. For our project, we chose a power squat rack, a common exercise equipment that has many main uses. Specifically, it holds a barbell between uses when the user is either doing deadlifts, rack pulls, or squats. This holds the bar so that it is in prime position to reset and be ready for the user's next set. It also has safety brackets seen at the bottom of the image that catches the bar in case the user fails during their set. In addition, it also has a section for weight storage at the back. At the top, it has a section for pull-ups or other body weight exercises in a hanging position. And additionally, both inside and outside of the rack, it has two positions where the user can either work out inside or outside of the main enclosure. Our primary and secondary customers would be small gym owners and home gym owners, respectively. For small gym owners, they would be ordering a number of racks at a time in order to support their business. In addition, they would be ordering more and more racks as their business scales, being a reliable business partner to come. Their expected total volume would be 1,800 racks a year. Secondarily, we have home gym owners who would order a smaller volume of racks, and their total estimated value would be 450 racks per year.
Our functional analysis was diagnosed using a FAST diagram. Our task function overall is to simplify exercising. Our primal basic functions are to store our equipment and add feasibility. To store our equipment, we add weights and then contain the weights. For our feasibility, we allow our users adjustability to the overall mechanism and connect support bars. To assure dependability, we have structural implications which increase the rigidability and also our safety concerns. We assure convenience, we add a ground anchor point, and we enhance the overall user manufacturability. To enhance the product, we add additional product features which will simplify exercising further, and also to please senses.
Here we have our assembly sequence analysis that starts, the first one on the left starts with a bottom x-axis support and a z-axis support bar. On that, added to that is an adjustable x-axis support, two of them, with an adjustable x-axis support with the cantilever beam style. Then, the weight plate storage bar, the barbell, and plates are added. The second part is the same thing except with the first two steps switched. So first, an adjustable x-axis support and an adjustable x-axis support with the cantilever beam is added to a bottom x-axis support and a z-axis support bar. Then the weight plate storage bar, barbell, and plates are added to it. Those two designs are almost exactly the same, but the only difference is the first two steps are switched. Thank you.
This is the bill of materials for our initial assembly. The total amounts to roughly $1,550. One thing to note, however, is that the M18 bolts amount to more than half the cost of the rest of the materials. This cost can be drastically reduced by using cheaper bolts rather than using the bolts from McMaster-Carr. As you can see in the quad chart, as mentioned in the previous slide, the bolts are the main cost in this assembly. We did not, however, feel that it was necessary to redesign the weight storage rack or supports, since they are such an integral part of the design and provide the backbone of the squat rack.
Here you can see a diagram of our functional component mapping matrix. As you can see, the function of storage has a total of 5 parts that are fulfilling it. The function of safety has a total of 2 parts, and the function of increasing rigidity has a total of 4 parts. We can also see that there's a total of 4 parts that are fulfilling more than one function. An ideal functional component mapping matrix will have a one-to-one relationship with the functions and the components.
In this slide, you can see our primary user rack in Figure 6 compared to Figure 7, which is our secondary user rack, which is a lot more mechanically feasible. Lastly, in Figure 8, our primary user rack base Our central safety beam and our main vertical support are completely different. They're changed in the way that they are attached to the bottom. We use a base support connector as one in our secondary design support, but in our primary one we used two. In our base support connector we also use two, but in our secondary design base support we use one. This is to help the overall manufacturability and usability of the overall weight rack.
This spreadsheet shows how much time is taken for manual assembly. At roughly 254 seconds, the rack does not take much time to design, as it is fairly modular in design already. However, one thing to note is that the base supports take too long to insert, and amounts to about 25% of the total assembly time. Hence, our redesign is fairly simple. The old design required 3 interlocking parts along with 4 bolts, 4 nuts, and 8 washers. The redesign requires no fasteners and only 3 parts.
For the automated part of our assembly, we chose to focus on the weight holders. Priorly, they were assembled using a nut at the end, which we found was very inefficient cost-wise after running through the cost analyses on a part to be automated. After running through the automation guidelines, we drew specific inspiration from number 2 and number 11, and instead came up with a quote-unquote lock and key method, where you insert the cylinder with a flange at the top, and then it is rotated downward so that the cylinder can no longer move and it is locked in place. This is all done by machine, hence the automation, and we found that this dropped our total assembly cost down to half after enabling this one feature.
The process selection for vertical supports goes as followed. Sheet metal forming is the ideal manufacturing process based off of the material, batch size, and overall custom nature of this manufacturing process. The material that we are using is carbon steel, which is a non-ferrocious material. The shape is prismatic, non-cylinder, and we estimate the mass between 8 and 9 kilograms per vertical support. The tolerance is 0.4 millimeters, which will allow us to join to the base, and our overall batch size is less than 2,000. The process selection for the weight holders goes as followed. Die casting is an ideal manufacturing process based off of the material, batch size, and repeatability of this part's manufacturing process. The material we are dealing with here is still carbon steel, which is a non-ferrocious material. The shape is prismatic and circular. We estimate the mass between 0.5 and 1 kilogram. Our tolerance for this part is 2 millimeters. Our batch size is less than 2,000, as well as the vertical holder.
Here's our design for manufacturing slide, and in our redesign we omitted the need for fasteners, which greatly dropped the time and cost needed for automated manufacturing. The original cost estimation of the materials for one unit was $1,550.67. After subtracting the bolts, we dropped that value to $566.07. The original cost of manufacturing was $978.13. The redesign cost was $692.67.
For the service, we decided upon a technically minded personal trainer, someone who can both maximize the potential of the squat rack as well as help any potential users use the squat rack. For the primary user, the technically minded personal trainer would be someone who would prioritize maintenance of the machine as well as help anybody who can use it directly. And for the secondary user, the personal trainer would be someone who did one-on-one coaching, helping the home gym owner maximize the potential of their squat rack. In conclusion, the redesign saved us a total of $1,270 and allowed us to reach a new customer market due to the smaller footprint and lower cost of the second variant of the racks. One improvement that we definitely want to make going forward would be having more impressive innovations. Given more time, we believe that product differentiation could be done better and at a greater scale.